We're going to learn about exoplanets today. I know we may have already started a little bit the other day, but I wanted to start fresh again. So exoplanets can be found outside of our solar system. And by the way, I want you to go ahead and open up a brand new Notability file and call it Exoplanets. So that you have a spot to take some notes. So define it. Okay, and then we're going to talk about ways to find them. So that's what you want to jot down and be ready to take some notes there. Okay, so they're outside our solar system, and that makes it very hard to find. As a matter of fact, when we discovered, William Herschel here, when he discovered Uranus, which took, by the way, until 1781, he was using a telescope. So he just used his eyes, right? It was an optical telescope. And he just saw it and was actually lucky that he saw it, because if you take a look here, how long it takes each of these planets to go around, right? Here's us, of course, 365 days. But Uranus, look at that, 84 years it takes it to go around the sun. So the odds of us being lined up so that we can see the planet in the sky, that the weather is cooperating, and that he was looking in the right direction is pretty amazing, actually. So it's hard to find planets even in our own solar system. So to find planets outside our solar system is even additionally challenging. Some other notes here that Neptune was found actually mathematically because there were some deviations in Uranus orbit. So we didn't even see Neptune with a telescope. They just found it kind of on accident. This guy said, look at that. The orbit is not right. Something else must be there. Okay, let's take a look here. Actually, I'm going to go back. I had these slides a little bit out of order. So here are some of the main ways that we can find exoplanets. So if you want to jot this down in your notes, radial velocity is one way. We're going to talk about what that is. So leave a little space next to each of these so you can jot down just a little bit about how it works. Microlensing, we're not going to talk a whole lot about that. Transit is one of the main ways. We're going to talk about that a lot. And then direct imaging is one of the other main ways that we find exoplanets. Radial velocity, microlensing, transit, and direct imaging. Okay, we're going to talk about each of these, so if you didn't quite get them, you'll have another chance. This is what we would call transit. And you can think about if you were in a movie theater and there's light coming from the projector and that goes to the movie screen, and somebody walked in front of it and they were blocking a little bit of the light. This is a very similar idea here. Imagine measuring the amount of light that hit the movie screen, and then if you could measure it again while the person was blocking a little bit, and you would say, oh, hey, there's a little bit less light on the screen. Same thing happens here. Scientists look at the brightness of a star, and then they look to see if there's any dip in the brightness at all. And then they can tell that there is a planet that is transiting around that sun. They can say, hey, something went in front of it. It's blocking out a little bit of the light. Here's a nice little illustration of that. Oops. There it goes. So they measure the brightness, the planet goes in front, the brightness dips. Simple as that. Another way that we can find exoplanets is through radial velocity method. And basically what happens is not only does our sun pull on us, right? But Newton's third law would say we pull on our sun, right? And so if there are objects orbiting a star, it will cause that star to wobble a little bit. And so you can see here in this little paragraph on the side here, the star will wobble backward and forward in the line of sight. And the speed of how much that movement can be determined by using the Doppler effect. So when there's light from an object moving toward us, it's going to appear blue. You might remember this from physics, for those of you that have had physics already. That's called blue shifted. Light that is moving toward us is going to be blue shifted. And light that is moving away from us is going to be red shifted. And so scientists can determine then if a star is wobbling or moving to and fro, and they can take a look at it and make a determination if there is something indeed orbiting that star based on the red and blue shift that they can observe. This one here on the bottom is the star's velocity as it's moving to and from the Earth. So you can see it's just translated from the image above in days. So it's the star's velocity toward Earth. So you can see the positive velocity and the negative velocity. And then this is just time on the bottom. Take a look at a little explanation here.
The radial velocity method uses gravity to detect planets. Remember, a planet is much smaller than its star, but it still exerts a tiny gravitational pull or tug on the star as it orbits. Now, when a planet is behind the star, from our point of view, it pulls the star slightly away from us. When it's in front, it pulls the star slightly towards us. And this causes the star to wobble back and forth. Astronomers look for this wobbling to find planets. Now, how do astronomers detect this wobble? Well, they use something called a spectrograph and a powerful telescopes to examine the light coming from distant stars. A spectrograph is like a prism. It splits the light from the star into its component colors, producing a spectrum. Some of the starlight gets absorbed as it passes through a star's atmosphere, and this produces small, dark gaps or lines in the spectrum. As the star moves closer to us, these lines shift towards the blue end of the spectrum. As the star moves away, the lines shift towards the red end of the spectrum. And astronomers can look for orbiting planets by looking for these back and forth motions of the lines in a star's spectrum. And that's how they come to know that there is a planet orbiting a distant star. And that is how the radial velocity method works.
Okay, so the star spectrum shifted blueward or shifted redward. So they can just tell if there's a wobble and then if there is a planet orbiting that star. Moving on, we've got a couple different exoplanet types. You can see them here. We have gas giants, which are just like our gas giants, size of Saturn or Jupiter, or sometimes much larger. And they have this term here called a hot Jupiter. And in our solar system, like we learned earlier in this unit, the heavier objects, like the rocky planets that we live on, tend to form closer to a star. And the lighter gas giants tend to form further out because of the outward motion of the radiation and the blasts coming from the early birth of that star, and it kind of blows all of the dust out of the solar system, leaving the heavier things toward the star and the lighter things out toward the edges. So from perspective of our solar system, it's odd for a planet like a Jupiter-sized planet to be very close to its star. But they do exist. So these hot Jupiters orbit very close to their star, but they're really, really big. And then you can see here we have the other ones. We have terrestrial size, so ones that look like Earth. We have ones that look like Neptune. And they have helium-dominated atmospheres. We have super Earths that are indeed rocky, but they're much bigger than Earth. But they're lighter than Neptune. So not super duper detailed differences here, but I want you to jot down the 4 different types. So you've got your gas giants, your terrestrial, those are the smaller rocky ones, kind of like where we are right now, the ones that are like Neptune, and then the ones that are terrestrial but really big. So those are the 4 types. You might want to note too that with the super Earth, it may or may not have an atmosphere. And when they call it a terrestrial one, they say here some could have oceans, they could have atmospheres, and maybe other signs of habitability. So maybe it's, close to its stars, so it's nice and warm. So you can jot down just a couple things to help you remember the difference between those. These are, at the time that I found this image, where the types of exoplanets that have been found. And what I want you to notice here is that the orbital period, so how long it takes it to go around its star, and then also on this axis here is the size relative to Earth. So Earth-sized ones would be here, and then they get larger as it goes this way. What you'll notice is that they completely tend to cluster toward Earth size and very small orbital periods. It's be very hard for us to detect something that takes 1,000 years for it to go, or this isn't days, 1,000 days to go around its star, because we're waiting years, right, for that to happen. Several years for it to just cross in front of its star just one time. It's obviously going to be much easier for us to detect stars that are orbiting very quickly, or I'm sorry, exoplanets that are orbiting very quickly around their stars, right? Because we have more chances to see them. So you can see we've got the rocky planets. There's just tons of them in the background there, and then hot Jupiters too. We can find those because they're big, but they also have a very short orbital period. Kepler, when you go to search your own exoplanet, which you are going to do today, was a telescope that we had that was looking just for exoplanets. It's no longer collecting data at this moment, but it got the first giant batch of exoplanets that we had found. And so this is just showing a habitable zone. And what that means is sometimes you'll see when you start to look up about an exoplanet that you're going to research, sometimes you'll see the word habitable zone, and sometimes you'll see the word Goldilocks, a Goldilocks zone, and that just means like it's comfy for humans, So Earth here is in the habitable zone, and that's this green part. Mars is too. And Venus is on the edge of it. But sometimes you'll see, like, if you look up here, these exoplanets up here are orbiting really close to their star. They are not in the habitable zone. That would not be a pleasant environment for humans. But these two are in the green. They're in the habitable zone. So, if they had water and if they had an atmosphere, they're at a nice distance from their star to where it's not too hot, not too cold. And that's why they call it a Goldilocks zone. The story about the bears and the porridge, that's just the right temperature. This is an illustration of how scientists might use the wavelength of light to determine whether or not there's an atmosphere. So when they've got a thicker atmosphere here, you can see the wavelength changes drastically. And when there is a thinner atmosphere here, you can see the wavelength is not quite as defined. So what you're going to do today is you are going to pick your own exoplanet. You're going to learn about it, become an expert about its orbital period and its habitable zone or not, its size, how far away it is, how it compares to Earth, Mars, Jupiter, or Neptune in size. And then you're going to try to convince people to come to your exoplanet just like they did in Interstellar, where they picked out planets and they said, yep, these are the ones we want to go to. Now, it's okay if your planet is not a nice place for humans to be. You can still pick that planet. It's fine. We're living in a fiction world here anyways. So let me show you the Exoplanet Instagram template. This is shared with you. And here are the instructions. You'll be researching your exoplanet and creating a travel, like a little, oops, changing the size of that, a little like you're a travel agent, and you're going to have a fake Instagram account here for the information that you find. And so you don't want to like pretend like you're working for a tourism company and you make money if people come to your exoplanet. So the first thing you want to do is find the basic information, as you see here. What is the name? Is it in the habitable zone? The radius, the orbital period. You can find all of that on the internet. And then you got to get a little bit creative. You got to sell it. How do you convince people to come? So you can show this using in the conversation speech bubble if you want to do that, like under the description. And then you want to have some photos. So I want a minimum of 4 posts or story frames. So either photos, like an artist's rendition of what the planet would be. You can have like some sort of computational model or a video of the transit. You can also just have other stock images. Like if it's a really hot place, maybe you have pictures of palm trees or something like that. So I want it clear. I want to make sure it's very prepared, interesting, informative, and your points are there on the side. I made one as a little example for you. The name of the planet is Kepler 101b, and I called my Instagram account Earthy Kep, as you can see there. I said how far away it is. It's 3,025 light years from Earth. And I showed how big it is compared to Neptune. And then I put a little comment there. I filled in a heart, a little like for myself. And I said, Goldilocks, baby, we're in the habitable zone of Kepler 101. So we are just right for all your galactic travel needs. We have water and nice temperatures. Come check us out. And then I would have like a couple more, add in a few more pictures. You're just going to copy paste the top part. And then if you wanted to have a pretend little conversation back and forth with somebody that you're booking to travel to your exoplanet, that's fine. And I'm not assuming that you will finish this today. Everything is linked on the agenda.